But what if the geometric sequence or series was not infinite? We wouldn't have had this. The only reason we got this far was because it was infinite, and infinite stuff are weird, right? So let's look at if it was finite. I'm not gonna go over the proof for this one because it seems kind of annoying and I don't really. Yeah, so let's look at this. A plus AR plus AR squared plus dot 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 up to AR to the N. Actually, let's do A up to AR to the N minus 1. How can we do this? We can obviously factor out an A, but then 1. So, I'm not gonna go over it. We have A times R to the N minus 1. Remember N, and this N, it's N is just how many terms there are, okay? That's why I did N minus 1, because it's the A to the R to the 0, A times R to the 0. And on the bottom we have R minus 1. Actually I can go over the proof. It's not that hard, like you always say that. Yeah, we can also switch it, so that's also equal to A times 1 minus R to the N over 1 minus R. This is better if R was a fraction, right? Or a weirder number that was less than 1. So now I'm gonna go over the proof. So first of all, we know that from algebra 1 that R to the N minus 1 we know is equal to R to the N minus 1 to the N, which is R minus 1 times 1 plus R squared plus dot 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 plus R to the N minus 1. And hey, guess what? This over here is equal to S divided by A. That's such a coincidence, right? So what we have here is that R to the N minus 1 equals S over A times R minus 1. Wow, we can divide by R minus 1 to get, and then multiply by A to get S is equal to R to the N minus 1 over R minus 1 times A. Oh my god, that's so crazy. Now, don't memorize any of these formulas. Well, you can, but there's no point. I'd rather have you know the proofs, because to be honest, they're not that hard. You can always just go step by step, and you'll get more with it, like a problem-solving strategy, right? So yeah, that's cool. We're gonna talk about recursive ones in a bit, but let's talk about some special arithmetic sequences or series. First of all, there's obviously the normal 1 plus 2 plus 3 plus dot dot dot, which I wanted to do earlier, right? Because we found a really weird way of finding the sum of that series, but we didn't know how to evaluate this ugly thing. How do we do this? We can solve the normal arithmetic series. We add the outsides, right? 1 plus n is n plus 1. 2 plus n minus 1 is n plus 1. So on, so on. And there's n over 2 of them. So this is equal to, or we can do our other method, right? To get n times n plus 1 over 2. I can expand that to get n squared plus n over 2, but this is much easier to evaluate. And now we can also do a bunch more. We can do 1 plus, we can do 1 squared plus 2 squared plus 3 squared. We can do sum of squares. I won't go over the proof. You can go over the proof using induction. Because after this you're gonna know it, so you can use induction to prove it. And yeah, it won't be too hard, don't worry. So if we add this, what we're gonna get is n times 2n plus 1, or n plus 1 times 2n plus 1 over 6, I think. Yeah. So now let's do sum of cubes. Yes, sorry, sum of cubes. Yeah, okay, this is right. So now sum of cubes, we can always continue, right? Sum of fourth powers isn't really necessary. Sum of cubes, you're probably gonna need this because this is so cool, and competitions like to use cool stuff. So yeah, you might think this will be really ugly, but turns out this is n squared times n plus 1 squared over 4. Now you might notice this, you feel like, oh, that's so familiar. It is. It's n times n plus 1 over 2 squared, which means that the square root of 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus n cubed equals 1 plus 2 plus 3 plus so on plus dot 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 plus n. That's cool, right? So yeah, you can keep going if you want, but it's not necessary. Yeah, so that's it on that. Now let's talk about recursive series sequences. Recursive series are ones that depend on the other one. So like the Fibonacci one is the Fibonacci sequence goes 1, 1, and then 2, 3, 5, 8, 13, 21, and so on. What's the pattern of this? You might not see anything arithmetic or geometric. But so what you do is you start off with 1 and 1, and every next term is the sum of the previous term. So 2 is 1 plus 1, 3 is 1 plus 2, 5 is 2 plus 3, 8 is 3 plus 5, so on. And I'm not gonna go over the sum or the pattern. There is a weird like formula for this. Yeah, the best thing to do in recursive sequences is to kind of eliminate something and then to kind of like get a normal sequence, a series like that has a normal formula. For example, if we have so typically recursive series and sequences are defined like this: a naught is equal to 1, and then n plus 1 equals 2a times n, or 2an. So like you have the starting term and then they give you the general formula for everything after that, or starting terms sometimes in Fibonacci. So now in this case, if we list it out, you might think, oh, what are we going to do? We have 1, we have 2, then we have 4, we have 8, and so on. You can really just kind of see the pattern. It's really that, so we can define it like this, or we can define it like an equals 2 to the n, right? So yeah, that's cool. If we started with a 1, some of them start with 1, some of them start with 0, then we'd have 2 to the n minus 1, alright? So yeah, sometimes we don't even start with a starting term. We might start with, let's say, the fourth term or something, right? So yeah, what if we had, we're not, it's not always going to be this simple though. It'll be something like that. Sometimes it's a quadratic. That's kind of annoying. You could try eliminating something, right? Find some pattern and then find some relation and then eliminate, right? Elimination and recursive and like pattern finding is really big of a deal. So in this case, what are we going to get? We're going to get 1, 2 times 1 minus 1 is 1, 2 times 1 minus 1 is 1. Oh, looks like it's just 1. Wow. See how much it changes? Right? It changes the whole thing. So yeah, that's, oh yeah, one more thing. Nested stuff. What is a nest in math? It's really when you have a repeated thing forever. Like, what's the square root of the, sorry, no, that's not gonna work. Oops. What's, the square root of 2 times the square root of 2 times the square root of dot dot dot? Well, how are we gonna solve that? Let's say that's equal to x. Notice that this whole thing is the same as this tiny thing over here, right? Why is that? Because it goes on for infinity, so like there's no end. So what we can say is that the square root of 2x equals x. We square it to get x squared equals 2x. So x equals 2 or x equals 0. Either we can check for extraneous ones, which we don't find. We can't, typically you might find an extraneous one if you find it negative, but we can't. They're both true. But you might notice that 0, you can't have this equal to 0. It just makes no sense, right? So the answer is 2 in this case. The answer to this problem is 2. It won't always be like that though. What if you had the square root of 2 to the square root of 2 to the square root of 2? That one seems a little harder, right? What are you going to do about it? Remember, this thing is the same as this thing, because they both go on for infinity. So you can have, so let's say that's equal to x. You have the square root of 2 to the x equals x. So you have 2 to the x over 2 equals x. So we have log base 2. If you know logs, right? Log base 2 of x equals x over 2. You could also just find out that 2 works out, right? But let's say I just guessed and check. But you can do the log thing to get log base 2 of x equals x over 2. 2 log base 2 of x equals x. Log base 2 of x squared equals x. 2 to the x equals x squared. From this you can guess and check easily, right? 1 works out also, right? No. Wait, does 1 work? 2 to the, yeah, no, sorry, 1 does not work. 2 works, right? Does negative 2 work? No? Okay, yeah, so I think 2 is the answer, right? Yeah. So log base 2 of x squared minus x. You can continue doing log stuff. I might be doing something wrong. There might be an easier way. Yeah. But notice something. What if we add the 4th root of 2, I think, right? To the 4th root of 2, you get the point. That's equal to x. You have x to the, you have the 4th root of 2 to the x equals x. So you have 2 to the x over 4 equals x. So, solve this. You can do a similar thing, like guess a check or whatever you want. There was another thing that was like really weird. I think it was, wait, no, never mind. So yeah, remember nested things, right? They have to be possible, right? They're not that hard. They might seem like it's infinite. They might seem mind-boggling. But yeah. Oh yeah, one more nesting. What is 1 plus 1 over 1 plus 1 over 1 plus ... This one might seem mind-boggling because you don't know where to start, right? There's no end. The end is the start, if you think about it. So watch that. Let's say that's x. Remember, you can look at the smaller part. So 1 plus 1 over x equals x. Multiplied by x, you have x squared. Remember, x can't be 0, right? So x squared plus, no, sorry, x squared minus x minus 1 equals 0. So x equals 1 plus or minus the square root of 1 minus, so minus 4, or plus 4, which is 5 all over 2, which is a golden ratio. Or 1 plus root 5 over 2 is a golden ratio. So yeah. Cool. There's much more to this, but I won't go over it today. So, thanks for watching, and I'll see you guys later. Bye-bye.